Okay, this lesson is on inverse functions, but before we can find the inverse of a function, we need to know what a one-to-one function is. The definition is here. For a one-to-one function, each x value corresponds to exactly one y value, and each y corresponds to exactly one x. Let's see a couple examples of that as to what a one-to-one function is. If I take, for instance, y equals x squared, and I were to make a table of points, a few points I could pick would be -2, -1, 0, 1, 2. And the corresponding y values would be 4, 1, 0, 1, and 4. Okay, those are just a few points that y equals x squared goes through. Now notice that when x is -2, y is 4. But also when x is +2, y is also 4 again. In other words, the 4 has been repeated. In other words, I have two different x values that go to the same y value. They both go to y equals 4. And so this is not one-to-one. The simplest way of trying to explain what a one-to-one function is that no x or y can repeat. And we have a repeating y's here. So y equals x squared is not a one-to-one function. Y equals x cubed. If I plot a few points that y equals x cubed goes through, it goes through -2, -8. Plug in -1 and I get -1, 0, 0, 1, 1, and 2, 8. And there are, of course, many others I could write down. Notice that no matter what x I pick, it goes to a different y, and no y is repeated. Even if x is -2, it goes to -8. If x is +2, it goes to a +8. So each x goes to its own y. Each y goes with its own x. There's nothing that's duplicated. And so this function is one-to-one, a one-to-one function. Here's another example. Suppose our function is just a set of ordered pairs. Suppose we have 1, 4, 3, 5, and 0, -2. Since each x goes to its own y, nothing is repeated. X is 1, x is 3, and x is 0. Y is 4, y is 5, and y is -2. There's nothing repeating. This would be a one-to-one function. On the other hand, let's fix that. Suppose we had a function f equals 1, 3, 2, 5, and 4, 3. This one is not one-to-one, and that is because we have a repeating value. 1 goes to 3, but 4 also goes to 3. Therefore, it's not one-to-one. Another way to tell if a function is one-to-one is to apply the horizontal line test. A one-to-one function will intersect any horizontal line at most once. Here are some examples of that. If I graph y equals x squared, we get a parabola. Looks something like that. If I draw horizontal lines, the horizontal lines will intersect more than one time. They intersect twice, actually. And so this graph fails the horizontal line test. Therefore, this is not one-to-one. y equals x cubed. If I make a sketch of y equals x cubed, it looks something like this. If I draw a horizontal line wherever I want, no matter where I draw the horizontal line, it will only cross the curve at one point, only one time, and so this passes the horizontal line test. This is a one-to-one function, one-to-one. Here's another example. Suppose I have a graph that does this. Notice that if I draw a horizontal line right in there, it crosses more than once, and therefore this is not one-to-one. And one more here. This is an exponential function, curves upward. Notice that it will pass over a horizontal line test. No matter where I draw a horizontal line, it will only cross once. And so this function is one-to-one. One-to-one. Okay, that's how we tell if a function is one-to-one. It has to pass a horizontal line test. Now, if a one-to-one function f is the set of all ordered pairs x, y, then we have an inverse function, f inverse. This is the symbol for it. And it is the set of all ordered pairs y, x. In other words, to find an inverse function, what we're going to do is just switch the x and the y. Find the inverse. Okay, all we're going to do is switch the x and the y. Let's say we have a function here that consists of the ordered pairs 1, 3, 2, 0, negative 4, 5. To find the inverse of this function would be very simple. The symbol for f inverse is this. It looks like a negative 1 exponent, but it's really not. You just read this as f inverse. F inverse. Just switch the x's and the y's. So 1, 3 becomes 3, 1. 2, 0 becomes 0, 2. And negative 4, 5 becomes 5, negative 4. And I found the inverse function, f inverse. Very simple to do. Let's sketch these and see what they look like. One, two, three. Not quite enough room here. Okay, let's sketch the function f first. We'll do this one in blue. 1, 3, 2, 0, and negative 4, 5 would be way up here, way up there. Make it a little bigger. There they are. Okay, so in blue we have the function f. In red, we're going to graph f inverse. 3, 1, 0, 2, and 5, negative 4, which would be 2, 3, 4, right around here somewhere. Okay, so in red we have f inverse. Notice that the function f and f inverse are somehow related to each other. The relationship is, draw that a little straighter. If you draw in the line y equals x, the function f and f inverse are reflections across the line y equals x. They are a mirror image of each other. And this is always true of a function and its inverse. F and f inverse are reflections about the line y equals x. Okay. Here's another example. Find the inverse. Let's take f of x equals 2x minus 3. And we're going to find the inverse. Now what I do, let's change that to a y first of all. Now remember, what we do to find an inverse is we switch the x and the y. So we're just going to switch x and y, which would look like this. X equals 2y minus 3. Then I solve for y. Solve for y. So x plus 3 equals 2y. And if I divide both sides by 2, I get y equals, I gotta put that 2 under each part here, 1/2 x plus 3/2. So if this is my original function f of x, then what I have down here is f inverse. So this is f inverse of x, 1/2 x plus 3/2. That's the inverse function. Inverse functions sort of undo what the original function does. For instance, if I plug in, let's say, 0 for x in the original function, I get f of x is -3. In other words, f of 0 equals -3. Now, if I plug in -3 in the inverse function down here, f inverse, if I plug in -3 in here, I get -3 over 2 plus 3 over 2, which is 0. In other words, f inverse of -3 equals 0. So it does the opposite. Up here, if I plug in 0, I get -3. If I plug in -3 down here, I get 0. Inverse functions always do this sort of thing. Now let's graph these. The original function f of x is 2x minus 3. So that's just a line. The y-intercept is at 0, -3, which is right here. And the slope is 2. And so I'm going to go up 2 over 1, up 2 over 1, up 2 over 1, and so on. And connect the dots as straight as I can here. There. Okay, good enough. Okay, so that's the function f. Now, f inverse is another line, and it's going to be the reflection of f across the line y equals x. One way that I could graph the inverse function is just to switch the x's and the y's. For instance, this point right here is at 2, 1. That means the inverse function must go through 1, 2. If this is 2, 1, then this has to go through 1, 2. This point right here is at 1, -1, and so the inverse function must go through -1, 1. This point here is at 3, 3, and so if you reverse those, you get 3, 3 again. And so the inverse function goes through there, 3, 3. And this point down here is at 0, -3, and so the inverse must go through -3, 0. Right there. Connect the dots, and you have f inverse. Notice that they are mirror images of each other, reflections across the line y equals x. And so we found the inverse function, and we've graphed them. Okay, let's try another one. Let's take a look at f of x equals square root, excuse me, square root x minus 1. Okay, to find the inverse, I'm going to switch the x and the y. So here I go, I'm switching them. X is here now, the y is here. And then now I'm going to solve for y. And to solve this equation for y, I'm going to have to square both sides, which gives me x squared equals y minus 1. Move the 1 to the other side, and I get y equals x squared plus 1. So if this is the original function, then the inverse function is x squared plus 1. There's the inverse function. Let's square them or let's graph them and see what they look like. Remember that a function and its inverse should be mirror images of each other across the line y equals x. So let's make a table of points up here for this original function, x and f of x. Notice that I can only start at, I can't start at 0 here because then I have the square root of negative 1. You can't graph that. This starts at 1. Plug in a 1, I get 0. If I plug in 2, square root of 2 minus 1 is just 1. If I plug in, let me skip to 5 here. If I plug in 5, I get the square root of 5 minus 1. Square root of 4 is 2. Okay. So if I plot those points, I've got 1, 0, which is here, 2, 1, and 5, 2. Our square root function looks like that. That's what it does. Okay, this is the function f. Our inverse function is supposed to be the mirror image or the reflection across the line y equals x. Now, if you take a look at our inverse function here, x squared plus 1 is a parabola which would have a vertex at 0, 1. Vertex is at 0, 1 here. And it would look like this. It would go through 0, 1, and then it also go through these points if you plot them. Just like that. Now, this parabola, of course, does not appear to be a reflection of the function f. There's too much of it. See, I only want this right side of the parabola. If I have that side of the parabola, to go through that point right there. If I have that side of the parabola, now those are mirror images of each other. That's what I want. That's f inverse right there. So, in other words, I only want this parabola when x is greater than or equal to 0. I only want the right side of it. So I have to put in here that this is the inverse function, but only when x is greater than or equal to 0. Because I only want this side from x equals 0 over of the parabola. Notice that this point is at 1, 0, and the inverse function goes through 0, 1. This point is 2, 1, and the inverse goes through 1, 2. And notice that this point is 5, 2, and the inverse function goes through 2, 5. They are inverses of each other by switching the x and the y. Let's do one more example of finding an inverse. Find the inverse. F of x equals x cubed minus 1. Okay, so once again, to find the inverse, I switch the x and the y, which would look like this. Switch. And then I solve for y. Solve for y. So solve for y, move the 1 to the other side. x plus 1 equals y cubed. And to solve that for y, I have to take the cube root of both sides. So y will be the cube root of x plus 1. This is my original function. What I have down here is the inverse. So f inverse is x, or cube root, x plus 1. There it is right there, the inverse function. Let's graph those and see what they look like. They should be reflections across the line y equals x. Let's plot some points here. The original function goes through the ordered pairs. Let's see, if I plug in -2, that'd be -8 minus 1 is -9. Guess I better go by 2's here. Okay, -2, -9. If I plug in -1, I get -1 cubed is -1 minus 1 is a -2. Plug in 0, I get -1. Plug in 1, I get 0. Plug in 2, and I get 7. Okay, so let's plot those points. -2, -9, 2, 3, 2, 4, 6, 8. That would be right around here somewhere. -2, -9. -1, -2 is right about here. 0, -1 is here. 1, 0. And 2, 7. 2, 1, 2, 3, 4, 5, 6, 7 is about there. Connect the dots, and we have our function f of x. The inverse function, which is down here, I can get either by making a table of points, or I could just switch the x's and the y's that are already here. Notice that this point right here is at 2, 7, so the inverse must go through 7, 2. 2, 3, 4. 7, 2 is about here. This point is at 1, 0, so the inverse has to go through 0, 1 right there. This point is at 0, -1, so the inverse has to go through -1, 0. This point is at -1, -2. Here, let's write these in. This one was at 2, 7, so this one becomes 7, 2. This point is at 1, 0, it becomes 0, 1. This point is at 0, -1, it becomes -1, 0. And this point is at -1, -2, and it becomes -2, -1, which would be right about there. And then finally, this point way down here, that point is at -2, -9, and so it will become -9, -2. Should be about here. -9, -2. Remember that the graph should be mirror images across the line y equals x. Keeping that in mind, if you connect the dots correctly, we get something that looks like this. And that is the graph of f inverse. Here's f and f inverse. And that is how we find inverse functions.